Okay, so thanks for the introduction, Ryan. I think that's the first time I've been called the grandfather of anything. Kind of like it, but a little ahead of time. So for those who don't know me, Josh Reiss, I'm a reader in audio engineering with the Center for Digital Music at Queen Mary University of London. And I'm also a visiting professor here, so I make frequent trips to BCU and really enjoy working with a lot of the research. So today I'm going to try to introduce at least some aspects of the topic that a lot of people will be talking about today, the idea of intelligent music production, and talk about it on a fairly high level, challenges, frontiers, implications, what does it mean, what will happen in the future, and of course with a bit of an emphasis on what the team of researchers working with me are doing. So there's this great quote by Alan Turing. Let's see, Alan Turing was visiting, this was during World War II, and he was visiting Bell Labs in New York and talking to Claude Shannon, another British researcher, but who was living in America at the time. And Claude Shannon, by the way, is the inventor of information theory. And if you don't know it, he's also the inventor of, let's see, the rocket-powered Frisbee, gasoline-powered pogo stick, a calculator that worked only on Roman numerals, and lots of other cool stuff. But Alan Turing, I think almost everyone knows about, one of the fathers of computer science, and Alan would talk about the brain, which is now known as the Turing machine, this theoretical computer, and use the concept to understand what can be programmed and what can't, and what problems can be solved or not. And then after lunch with Claude Shannon, he walked away a bit stumbling, confused, and he said, Shannon wants to feed not just data to the brain, but cultural things. He wants to play music with it. So way back in 1943, people were thinking about if there were computers that could actually do interesting things, what can we make a computer to do with music, and how far can we take it? So the motivation for a lot of this research is that music production is labor-intensive, it's difficult, it's technical, you need a degree to do it well, and it can be very challenging. And there are two sides to it. There's the very technical component, get all the microphones in the right position, calibrate things, deal with comb filtering, balance the levels of all of the sources, and there's the creative side of things. How do you get more out of the music than just a flat recording? What creative touches can you put on top of it? How can you take the musician's vision and amplify it through the production? And then sometimes you have producers and sound engineers who are who have just as much creative input into the music as the musician. So you have, say, two types of record producers. On the one side, you have people like Steve Albini, who say, I just try to reproduce what the artist wants me to. And in fact, he won't even call himself a record producer. He says, recorded by Steve Albini. On the other side, you have people like DJ Spooky, where the band or the musicians in the studio, they are his musical instrument to play with as he wishes. So what I'm getting across there, and I'm probably preaching to the choir on this, is the idea that this is not just a little icing on the cake. The music production is an integral and essential part of the whole process. But it's very difficult. There's often not sufficient resources to do it properly. How many of you are practicing musicians, maybe doing small gigs or large gigs around town? Okay. Have you ever had your band or your group's music ruined by the sound guy?
Yes. It just happened last week at the Greenman Festival.
What went wrong? I wasn't going to ask that, but now I'm curious.
Well, to be honest, what he did, it was not expected. We told him that the microphone that Joe, our band leader, is going to talk to is going to be also the microphone allocated for a solo saxophone. And told him, are you prepared? And we did the sound check and everything like that. He said, And there was a solo saxophone that only the fair 5 people that were in the front struggling to hear actually heard it. Oh,
Wow.
it was cool.
Although it wouldn't surprise me if you had just moved your lips like this. He would have said, yeah, everything's cool. Didn't really matter. I'm sure that was his response to a lot of things. But I think almost everyone who is a practicing musician, especially those people who have done small gigs, pubs and bars and things like that, will have a story or two, sometimes just last week, of gigs ruined by the sound man or of the sound problems in some sense ruining the gig. So sound quality very often suffers. Then there's another way of looking at the need and the desire for intelligent music production. Compare audio with video and image. So modern digital cameras, most people don't even have digital cameras anymore because it's all embedded in their smartphone. But even so, they come with a whole host of intelligent features to automate the process for the user. Face, scene, motion detection, red eye removal, image stabilization, autofocus, etc. These are completely standard now. Even professional photographers will make use of the features very often, and people would be very surprised if the camera in their phone or any digital camera didn't have at least most of these features. In contrast, digital audio recording devices in general have none of this. So I picked one at random and just looked at what, going to Curry's website or Amazon and just what was the marketing hype in the small amount of text there. Interactively guides a new user. You can't imagine a camera saying, we can guide the new user how to take photos with this camera. A retry function to help fix mistakes. Again, a camera, you don't need a retry function because it's not going to make those mistakes. And I love this last one. It can record anywhere. Can you imagine a camera trying to market itself to people saying this can take photos both inside and outside? So there's this huge gap between the intelligence in image and video technology and the intelligence in audio technology. Now I'm sort of cheating here because of course these are multi-track recorders and there's a lot of issues with the multi-track situation, but I think in general, you can get a digital microphone. There are very few products that could count as an intelligent microphone. So that's the whole challenge. Why isn't there an autofocus for audio? And when you think of an autofocus, you can think of it helping the sound engineer in setting up everything during the sound check. You can think of the musicians who just want to practice and want a decent recording while they're practicing. You can think of someone listening to music or listening to multiple channels of sound and wanting a good mix without even thinking in a musical sense, but just wants good sound quality on whatever's playing back sound for them. But really, this is the gap. There is nothing close to an autofocus. You can find a few research papers and a few technologies that scratch on the surface, but nothing like the purely intuitive, behind-the-scenes technology that you find with video. There's a few more motivations. So this now is quite old. This was an editorial in Sound on Sound, which is sort of the premier mainstream magazine. You can find it on the shelf at Waterstones or anything. And the editor said a few things in here. This was, by the way, it appeared right when we sort of started researching the area. So different people were saying the same things at the same time, but we saw this and we said, that's what we would love to do. And among the things he said, there's no reason why a band recording using reasonably conventional instrumentation shouldn't be EQ'd, equalized, and balanced automatically by advanced audio workstation software. So, in other words, there's a lot of tasks in production, like balancing the levels, dealing with electrical hum, dealing with some high frequency or background noise and things that could be just cleaned up without needing user interaction. And you can always have it as advanced features that can be turned off. You can always be able to modify those features or say, I want a little bit of it or not. But there's a lot of tasks that, in general, you would want done. And you can do it yourself, but it's a technical task. It's not requiring art and creativity. It requires the creativity if you choose to break these rules. But in general, these are just technical challenges in recording a good, clean sound. So, and then he went on to say another point here, which is quite important to the motivation and sort of how we pitch this whole idea. The musicians would rather get on with making music than get too deep into engineering. So if we talk about intelligent music production, or more precisely, autonomous music production, where there may not be an individual involved manually turning the knobs, rather there is a system listening to the sounds coming in and making decisions based on those sounds, based on some knowledge of what's normally done in a sound scene, embedded with some rules of sound engineering and so on. If we talk about that sort of thing, then you could look at it from a skeptical or critical mind and say, whoa, you're replacing the sound engineer here, you're getting rid of the talent, you're putting the human out of the loop. But you could also say this is for the musician. And there are many times when a musician might be performing and doesn't have access to a sound engineer, or you're providing a tool to assist the sound engineer. So it's not about replacing the sound engineer. There will always be need for talent, but it's about enabling people to have better sound in those situations in amateur productions. One time when I was talking with someone about this, and he couldn't get over that point, I asked, well, are you in a band? Yeah. Do you do practice sessions? Yeah, you know, once a week we all get together. Well, when you do those practice sessions, do you hire a sound engineer to make a good recording for you? He's like, well, no. So that's the sort of situation that intelligent, autonomous music production systems could be most effective for. And there were a few other points here. So audio interfaces can come with a gain-learn mode. The audio workstations could optimize their own mixer and plug-in gain structure while preserving the same mix balance. So once you define what the technical task is, and you define it in sufficient detail, then you can attempt to build algorithms to achieve that task. If you just say, I just want to make this a good mix, then it's hard to say, well, how is the algorithm going to make things good? But if you can come up with the rules and understand them, then if it's well defined, you can actually turn that into an algorithm, or at least hopefully you can. So why don't I pause here and give you a demonstration or a video of the sort of thing I'm talking about. So, not on screen, is it? Okay, so this video should sort of speak for itself. It should sound awful, and that's intentional because all the settings are off. There's no one has adjusted the levels or the input gains or anything. And we're going to turn on components of an intelligent music production system one by one. There's 8 tracks of audio coming in. They were recorded, but they're coming into this intelligent system in real time. So all the processing is real time on these tracks. So fingers crossed, you should hear decent sound. You should hear bad sound in a minute. Okay, so a bit more about that. Let's see if we, yeah. So a bit more about that. Just fast. Okay, what we had there was technology that was developed quite a few years ago, by the way, by a PhD student working with me, Enrique Perez Gonzalez, who is now Chief Technology Officer at SSL. So he got his dream job after his PhD. But he had the audio coming in and the levels were all off, so he had an automatic gain control on each of the input channels. Then automatic fader controls, where the trick in what they did is each channel analyzed the signal on all the other channels as well as itself. And so looked at the relationship between the levels on all of the channels, and based on that relationship decided whether to increase the level or decrease the level. This is a nice example of something that in a perfect world, the computer can do better than the human, at least in a live situation, because we are not octopuses. Octopuses? We can't move 8 hands at the same time, whereas the computer can vary 8, 16, 32, however many channels you want in real time simultaneously. And there were a few other things going on there, some equalization, an automatic stereo panning, and so on. And that was a great demo, but back then we had a problem, which is it sounded really good in that case, but if we just picked any sort of random multi-track and threw it at our system, it probably wouldn't sound good. That's one of these cheating demos where we say, look at what this can do, but we don't tell people that's what it can do, but we haven't figured out how to make it do that on other stuff yet. So that was a few years ago. There's been a lot more research since then. But that's the whole idea of a lot of the intelligent music production work. How much can you automate the process? Can you provide intelligent tools? Can you provide assistive tools? Can you make life easier for the sound engineers, easier for the musicians? Can you build technologies that are much closer related to perception? So rather than, say, just a set of compressors and equalizers with thresholds and ratio and attack and release and stuff, can you have things that control the muddiness in the mix, the clarity in the mix? Can you have things that basically just spatialize the sources rather than individual panning controls on each channel and dealing with a complicated routing system in a console? And so this sort of technology has 3 areas of use. Tools to assist the sound engineer, tools that allow the musicians basically to plug in or turn on the device and hopefully get decent sound out, and then embedded systems for consumers who aren't necessarily engaging with the device but just getting better sound as a result. So all of these intelligent systems, and by intelligent systems, we mean the textbook definition, a system that can perceive, reason, learn, and act intelligently. So it can intelligently configure its parameter settings. It can perceive what's going on in the sound scene and make meaning out of it. And it acts intelligently by dynamically adapting. But we did impose in this research some additional requirements. We were looking, and we still are looking, at post-production and live mixing and live recording. Ironically, the live situation is the easy one, because when we're comparing against human systems, in a live situation, it's very much a technical task. Usually the sound engineer behind the mixing desk is not trying to do something really creative regardless of the band. He's trying to ensure that they get good sound in the front of house and good sound on the monitor mixes and so on. Whereas in a post-production situation, it might be a sound engineer and record producer, a team of people working for a few weeks to create a perfect mix. Or even if not that, still they have the freedom to do whatever they want. So when we compared the systems we were building against post-production, we were far from from reasonable quality, at least in the early stages. So, but we did require it to work in live situations, so real time, and more than real time, we want it to work live, and that means minimal latency. So a real-time system could be something, it's New Year's Eve, and on your computer, you're watching the ball drop or the fireworks go off. And if it can cut, well, that's actually a bad example, because in that case, you do want low latency. You don't want at midnight it to happen, and then you just see it on your screen midnight and 5 seconds later. But there's a lot of real-time systems that you can interact with where it doesn't need to know the whole of the signal that's being analyzed or the whole of the content in advance, but they allow latency. Live music situations generally do not allow latency. And also, if we're looking at various different techniques that are quite established, say source separation, for instance, we need to use criteria that are very, very practical, not necessarily how much of a source has been removed or extracted, but just how good does it sound. And we can't allow artifacts to come into the system. So we've been looking at 3 different approaches, one which I'm calling grounded theory. Technically, it's slightly different, and knowledge engineering and machine learning. And so I'm going to talk about those 3 areas in the next few slides. But first, the architecture that a lot of these systems are using is like this. So it's based on something from around 2000, developed by Vincent Verfai and others, which is a sort of theory of audio effects, a classification scheme where Vincent talked about adaptive audio effects. And adaptive ones are ones where what they do to a signal depends on the signal. So if I see an equalizer and I can see the center frequency, the gain, and the quality factor, I know what that equalizer will do to any signal. I don't need to know the signal to know the type of effect the equalizer will have. But if I look at a compressor, I can't really tell what the compressor will do to a signal until I can see the signal that it's going to act on. The compressor is level dependent, and its behavior depends on that level of the signal coming in. So that's the idea of an adaptive audio effect. A cross-adaptive one is one where it doesn't just depend on the signal coming in, it depends on other signals coming in. So if we want to build some intelligent multi-track effect, we need to be able to tell what are all the different signals coming in. If you want to set the levels for the saxophone player correctly, then it would be nice to know what is happening on the vocal mic and on all the mics around the drum kit and so on, because you need to deal with masking and interference and crosstalk and so on. So the approach we've taken is based on these cross-adaptive effects, where we can have many different channels of audio coming in. We extract features from all of them. We look at the relationships between all of those features, and based on those relationships, decide the signal processing to happen on each of the tracks. All of the analysis here in the feature extraction and the feature processing is on a side chain. So audio is coming in without any delay coming out. The only effects being applied on those audio are the same effects that would happen ordinarily, like compressors and equalizers and so on. So that's the architecture that we've been using for most of this. And we started out much of the research where the constraint rules that we applied, because that's where all the challenges, by the way, is figuring out what to do to all of these tracks. The constraint rules came from best practices in sound engineering. For instance, and these aren't necessarily exactly how the system was built, we know that people generally don't hard pan their sources. They don't put them extreme right, extreme left. We know that vocal levels in general are kept a few dBs higher than other sources. And so we can put all these rules into the system. But we didn't verify the rules initially. We didn't necessarily know exactly how high the vocal should be in comparison to everything else. So we made it up. And if it sounded good, we kept it, and we started doing some subjective evaluation. So, where am I? The slide's being cut off a little bit. So as I mentioned, we're building these intelligent systems, autonomous systems. There is a slight difference between the two. Autonomous basically means it's without human guidance. And when we started doing this work, got a nice bit of press about this, trying to essentially call, I think New Scientist was calling it the robot sound desk. But we were looking from a basic research perspective. So how much can we automate? And then if you look at the practical applications, it's, well, how much do you want to automate? And how much of that automation should it be turned into monitoring, metering, or assistive systems? But yeah, the big question is, what are the rules and algorithms, and how do we establish them? Because one of the things we found out very early on is, if you, say, ask a famous record producer, what did you do on this album to make it sound so good? You get answers like, well, I turned the knob to 11 and it sounded fat. How do you turn that into a mathematical algorithm? Or there's one conversation I had with someone. We had a technology to prevent acoustic feedback, and I was talking to a live sound engineer trying to get an idea of what they were doing, because our system was modeling what we thought the live sound engineer did in acoustic feedback prevention. And I asked him, so, do you ever have feedback problems? No, never at all. Are you sure? Oh yeah, no, my gigs are great, all the mics are set right, never feedback. It's like, well, never at all? Okay, maybe once or twice. Well, tell me about the last time it happened. Well, yesterday. So, trying to just take the common knowledge or best practices and turn it into algorithms is very challenging. And even when the rules are there, they're not necessarily sufficient. So a lot of the rules will say things like, don't hard pan, but they don't tell you, well, okay, but how much panning should you do? And you have a lot of leeway within those rules, but it's still not enough to build a system. So the approach is, well, some rules are known. Maybe we can do some studies, some listening tests, subjective evaluation, etc., to get more rules. And maybe we can analyze all the content that is out there and extract the rules from analysis. Try to measure how high were the vocals in comparison to everything else in the mix and all these different recordings. So the first of those approaches is knowledge engineering. When people talk about intelligent systems, this is actually what was done way back in the past, 70s, early 80s and things. It's not cool anymore, because generally people found out with a lot of cases where you try and build a robot to do some task, the knowledge is insufficient. You also have a problem, a big problem, that the guys building the robots know how to build a robot, but if you're building a robot to, say, operate in a medical emergency room, just naming one up, the guys who are building the robot don't know anything about what goes on in the emergency room. So knowledge engineering systems most of the time didn't work, but there's a wealth of knowledge about audio engineering and sound production. And so we can use that where it's available. And this approach involves integrating all of this established knowledge, going through the textbooks, talking to sound engineers, record producers, getting a feel for what are the rules and which rules are commonly accepted, which ones are assumed but not actually correct, and so on. So that's mostly how we started. When we apply that to audio production, this is the sort of best practices approach that I mentioned a few minutes ago. And there's a lot of books on audio production, a lot of very good ones. But very often you can read a dozen of these books and they don't nail down this is exactly the recommended practice. And it's not just because it's so artistic. There might still be a sort of best first attempt approach, but the famous record producers don't always think outside looking at what they've done. Rather, they have an incredible skill, but they haven't necessarily translated that into an educational text. So there's also been very few systematic studies. There's been a lot of social science approaches and ethnographic work, but very little formalizing of the rules, and a lot of rules aren't very well defined. A mix should not sound muddy. That makes sense, but what is a muddy mix? So the second approach is grounded theory. Now, formally, grounded theory is sort of the reverse of the scientific method. The scientific method says, I have a hypothesis, a theory around that hypothesis, I do a test, and I accept or reject the hypothesis. The grounded theory approach, which happens a lot in practice even when people don't call it grounded theory, is I go out and talk to a whole bunch of people, I interview them, I collect data, and then looking at the data, then I make up my theory and my hypothesis. So you reverse it. You retrospectively form your hypothesis to fit your data. It's not really cheating because you're gathering the data in order to find out what might be a good hypothesis. So, but the idea is that coming up with the rules of audio production could come from doing a lot of tests, doing subjective tests, psychoacoustic studies. If we're unsure what is a good rule of thumb for how to set the threshold and ratio on a compressor for different content, do studies, take the people in this room and give them all sorts of different content to listen to and find out how they set it. So we're able to then form a theory based around that. And so this can supplement the knowledge engineering approach. We can start filling in those gaps here. But there's still going to be an awful lot of gaps that we don't have. So if we apply this to audio production, then yeah, it's a lot of psychoacoustic studies. The psychoacoustic studies are usually trying to find out how we perceive when do we notice a difference between threshold and ratio settings on a compressor. The perceptual audio evaluation studies are sort of, well, if the psychoacoustics you do at the beginning, the audio evaluation you do at the end. You build your system, and then you find out, do people actually like the sound? Did people prefer one compressor setting over the other one? So the drawback of this approach is it's very intensive. You have to do these big, careful studies in order to fill in a few of the gaps. But you do learn a lot in the process. The third approach would be machine learning. So construct and study of systems that can learn from data. This is the machine learning where you think, well, just feed in all these mixes into a system and let it somehow spit out the answer, this is a good mix. Or if a signal has these features, then it should be mixed this way, or this production should happen. And very often in the machine learning systems, the supervised machine learning, or those that you work on training, you don't need to know why, or you don't find out why it worked, it just worked on that content. So a big challenge with machine learning is that you need good data. If you've got enough data, hopefully your machine learning system can figure it out. But if it doesn't have enough data, it doesn't have anything to work with. And therein lies the big problem with applying machine learning systems on music. So we've done some studies where we analyze lots of produced music to try to find out things like what is the average spectrum on produced content, get an idea of sort of the overall EQ curve that might be applied. But what we'd really like to do is figure out what people are doing on the multi-tracks. And so for that, we need access to lots and lots of multi-tracks and to mixes of those multi-tracks and to some evaluation of those mixes to find out which things people liked and didn't like. And we need all the content to be varied, and we need lots of evaluation so that we get some overall idea of not just what you like or that person likes, but what in general people like. So we need a huge amount of training data, and you try going up to a record company and say, can you give us access to all your multi-tracks? I realize this is your most valued possession, but we promise to only use it for research. We're just lowly academics, but we're not going to let it get out there into the world. And as you can imagine, you do not get a positive response there. So, but those are the three approaches that can be tried and should be tried. And together, using all of those approaches, it should be possible to really gain some deep insight into music production. Because it's amazing that even today, despite all the research being done, there is very little understanding on a formal theoretical level of what makes a mix sound good. You may learn how to make a good sounding mix, but that's not the same as us understanding this is what makes the mix sound good. This is why one mix sounds better than another. It's still very much a creative thing where somehow at the end you are able to create good mixes, but we don't have a formal, deep understanding of perception of mixes, perception of audio production. So people have been looking at these approaches. Just going through a few of the papers, and this is terribly out of date, nothing from 2014 because I just updated it with a couple But there has been quite a lot of work. So the ones in bold are where people built an intelligent multi-track production system. Maybe it was only doing multi-track EQ or multi-track compression. The ones not in bold are ones where they contributed to our understanding of mixing and production. And there's a few people in the room who've done a lot of work in this area. Alex Wilson, he's done some recent work, I think this year, yeah, about it, but also some work over the last couple of years, gaining insight into preference for mixes and how it relates to features. Breck DeMann, who will be talking later, as well as Alex, has done a lot of work on semantics and analyzing lots of mixes. And Dave Ronan has been looking at grouping and subgrouping in mixes. One of the things to get away from this, though, is that in general, with all of the work, people have used just one approach. So maybe they've built a system based on knowledge engineering or a system based on grounded theory, but with very few exceptions, there's hardly been any systems that use both or all three of these different areas. There's work like Pedro Pestana's work where he analyzed a lot of stuff to gain insight, and he used psychoacoustic studies, and he used knowledge engineering approaches, but he didn't build a system based on it. So I think a hybrid approach would be the way to go. And you could do these sort of hybrid approaches using all three, filling in these gaps. You could, say, establish perceptual loudness models based on a grounded theory. And so you do some psychoacoustic studies, improving measures of loudness. You could build knowledge engineering systems based on our knowledge of how people already do panning and spatialization. There's a lot of knowledge there. And machine learning, and some of this, all of this, by the way, has been done in these different systems. Machine learning to analyze popular recordings and get this overall EQ. So just to show you a few of the interfaces, people have been building these different systems. This is automatic preamps, so gain controls, and they're automatic faders. This is a sort of improved version over the one I showed in that video. And a panning tool. It did both time delay and gain adjustments using a tangent law, which I think, where was Young Cook? I saw him a second ago. Yeah, so has probably a quite improved version of the tangent law, but used the tangent law for panning sources and knowledge, trying to essentially make as wide as possible of a mix while still keeping low frequency sources close to the center, not doing hard panning, ensuring a distribution of the spectral content, a distribution of the source of the individual sources, and a few other criteria. And an autonomous equalizer system trying to prevent muddy mixes. A delay correction, which is very much a technical challenge, so simply to align multiple microphones recording one source and variations on that problem. And automatic compressors, where there's been more work, and an automatic master EQ, so trying to ensure that the content has a final overall mastered EQ curve like popular recordings. And for all of this, we've been doing subjective evaluation, mainly listening tests, asking people to rate a whole bunch of different mixes of the same content. Well, I could spend an hour talking about this, but I just want to get one thing across here. These plots are fairly messy. And what that means is that a lot of these systems aren't working well. They're not necessarily performing as well as the professionals. They do a lot better in general than a very bad mix. We've gotten some systems that are getting close to professional, like a multi-track compressor system, got very strong results recently. But if we had great systems, you would see that our automatic system would always be up here, and the professional engineers would be around the same place. We've found many interesting situations. In at least one of our systems, we always ranked fairly good, whereas the professional most of the time was above it, but sometimes was actually worse, which meant we sort of went for a general average decent mix, but without the creative touches. So, but really what this is getting across is more work is needed. Anyway, I promised the title of the talk was, I think, Challenges, Frontiers, and Limitations. So, challenges, as mentioned, we need more multi-tracks. The more multi-tracks we have, the more analysis that can be done, the more machine learning approaches can be applied. We need a lot more evaluations. We're starting to build test beds of multi-tracks. We need more and more, but test beds of multi-tracks only go halfway unless you actually have evaluation of mixes of those multi-tracks to decide what sounds good and what doesn't. And we really are just scratching the surface of understanding the creative touches. What makes one mix make you laugh and another mix just sounds technically correct? Or one mix makes you cry, might be a better one to talk about. And this isn't an entirely new area. So James Maurer, you might have heard of Maurer's reverberator. He said in 2000 at a keynote address, what will arise over the next 20 years is the intelligent assistant to take over the mundane aspects of music production and leaving the creative side to the professionals. So maybe we don't have to address the creative stuff. It's an interesting academic question, but we can definitely focus on all the technical challenges. Frontiers is doing this hybrid approach, filling in these gaps and gaining a deep insight of what makes different productions sound different from each other, what gives them an emotional response, which may be talked about later on today as well. Why do people like one mix and not another one? I think we'll only gain the deep insights if we throw all of our approaches at the problem. And the implications, well, it is a little controversial. So I'm not going to mention who this was, but if you know pop music production, you might have heard of the record producer who said this. When he saw the New Scientist article about this work, he wrote, tremendously disappointed that you even thought this rubbish worth printing. And another record producer said, ridiculous waste of time and research. But I think the quote on, this was on some, it might have been KVR or Geosluts, one of the audio technology discussion forums. Someone said, I've had so many shows I played ruined by really bad sound mixers. And he said that, was it in this one? No, so another guy in the same forum said, as a sound engineer, I'm really uncomfortable with this, but as a musician, I love it. And the final quote is by Brian Eno, said, that was the era of musicians, while now is the era of producers. Today's great innovation is the studio, the recording process. And so I think the innovations that are going to come are all going to be, or a lot of them are going to be these technologies dealing in the mixing and the production. And I think on that point, I'll end it for today.